Good morning. Today we're going to get ourselves started on section 5.1. We're going to be dealing with two things here in this, actually for the first four sections are all going to be kind of the same. We're going to be dealing with roots and rational exponents. Okay? Now roots is just a word that's equivalent to radicals. So we're going to be dealing with different types of roots or radicals. That'll be the first thing. The second thing we're going to do is take a look at what are called rational exponents. So that'll be coming up just a little ways down the road. All right, first, this idea of roots or radicals really mean the same thing for us. Okay, and so that's, of course, we're very familiar with doing square roots and cube roots of different types of numbers. And so just going to talk that over slowly at first. First, for any kind of radical, we're going to have some definitions, some terms that we use for parts of the radical. So when we say them, everybody knows what we're talking about. First of all, the symbol itself, the symbol that we use for a radical, is just simply called the radical sign. So if I ever mentioned to you, you forgot to include your radical sign or something, that just means that symbol, which tells us that we're going to be taking some sort of root. Then, of course, there's going to be two numbers that we're going to be dealing with. We have the number that's inside, and that number that is inside is called the radicand. And then the last one that we're going to deal with is the type of root that we're talking about, whether it's a square root, cube root, fourth root, fifth root, whatever, it's going to be the type of root that we're dealing with. And that number, that little number in the corner, is called an index. All right, so those are some terms we're going to be using. The index is the type of root. The symbol itself is called the radical sign, and then the number inside is called the radicand. Change the suffix there. Okay? Alrighty, so those are some terms we're going to be using. And as I go through the video, if there's ever a time I'm going too fast, feel free to pause the video so you can take notes on whatever you think is necessary. One thing I've mentioned before, but I'm just going to mention it again because most of this chapter is going to be dealing with radicals. All right, I need to remind you of a shortcut we take for square roots. We use square roots way more than all of the other types of roots put together. And so like so many other things in math, we shortcut it. And so whenever we have a square root, that means the index is 2. And because we use those so often, we will very often not bother writing in the index. We'll leave this space, let me choose a highlighter here, we'll leave this space blank, and when we leave it blank, that means it is a square or second root. Okay? So when we write, as an example, the square root of 9, that means the second root of 9. Those two things are equivalent. Of course, we know that answer is 3. Okay? So anytime we have a radical without an index, that's automatically a square root. If we want any other type of radical or root, then we are for sure going to include the number. So if we want the cube root of 27, we for sure will show you the index of 3. Okay, and so on. Alrighty? Okay, so I'm going to get you ready for one of the problems you're going to see in your assignment. And what the problem will do is say, we are going to take the nth root of a. So the index is n, the radicand is a, and then they're going to give you different values. So just as a couple of examples to get you kind of the feel for this. If the type of root is a 3, and the number is an 8, this just translates then into just inserting those two numbers, replacing n with 3, a with 8. This just turns into the third root of 8, or cube root of 8, which of course is asking what number multiplied by itself 3 times gets you 8. So our answer is 2. Okay, just do a couple more examples just to kind of get you a feel for that. If this was a 3 and our number was 125, this just then would become the third root or cube root of 125, which of course is 5. Those are ones I've asked you to memorize. Okay? We can do some that are a little bit harder. Let me scooch this over a bit. We could do some a little bit harder. What if I gave you an n value of 5 and an a value of 32? This would then become the fifth root of 32, which is asking what number multiplied by itself 5 times would get you 32, and the answer is 2. Okay? Or I could try and trick you with one. We could give you an n value of 13 and an a value of 1, so this would become the 13th root of 1. So we're asking what number multiplied by itself 13 times gets you 1, which of course is 1. All right? And we can do the same thing, or something similar, I should say, with some negative a values. So let's just bop out a couple here. If I were to go back to an n value of 3, and we used an a value of, let's say, negative 64, this would then become the third root of negative 64, which once again is asking you what number multiplied by itself 3 times gets you negative 64. And the answer would be negative 4. Okay? Righty? So hopefully those aren't too bad. But please notice if I shrink this down so you can see them all at once, and I'll choose a highlighter so I can see. Please notice, oops, sorry, hit the wrong button. There we go. Please notice that the first batch of n's that I've asked you to work with so far have been odd. So when the n value is odd, so when n is odd, so 3, 5, 7, 9, 11, 13, and obviously so on, what we get as a result is 1 value. We get 1 value out. Okay? Unfortunately, well, you probably kind of know where this is going. What if n is even? What if n is even? Right? So what if we have a problem where we have n is equal to, let's just keep it easy, 2, and our a value is 16. Okay? Or what if we have n equals 4, and our a value is 16? Well, what this would then become is the second root or square root of 16, or this one would become the fourth root of 16. All right, so how does it change when n is even? And the answer is, instead of getting 1 value, we usually get 2 values. And you guys can't read that, so I'll write that out again. We usually get 2 values. And where do the 2 values come from? Well, we've talked about this one before. It comes from the plus or minus. So we get a plus and a minus option when we have an even root of a number. So the second root of 16 could be either plus or minus 4. The idea is, again, positive 4 multiplied by itself is 16. Negative 4 multiplied by itself is 16. So when we take the square root of 16, we should get either plus or minus 4. But then it extends to the fourth root, sixth root, eighth root, 10th root, and so on. So whenever n is even, we traditionally normally get 2 values out. So for the fourth root of 16, we get plus or minus, and then what number multiplied by itself 4 times gets you to 16? The answer would be 2. And I'll just do this kind of quickly. Because positive 2 multiplied by itself 4 times gets you 16, or negative 2 multiplied by itself 4 times gets you to 16. So if I take the fourth root of 16, I have to be able to get either positive or negative positive or negative 2. Okay? So just a little bit about roots, And then more important for us, and we're going to spend a lot more time on this one, what we want to be able to do is take different types of roots and turn them into what are called rational exponents. And we use this word rational a lot in advanced math, but the word rational just simply means fractional. So whenever you see the word rational in math, and we're going to come back and see it again in a couple of chapters, it really just means fractions. Okay? So what I want to show you is how to turn something with a root, a radical sign, into something that would have a fractional exponent. And here's kind of our general way to do it, kind of the formula, so to speak, is if I give you a radical, and I have the nth root, and a might be raised to a power, what this will then turn into as a fractional exponent, the radicand just stays the same, and then what we do is we create a fraction out of the two numbers n and m. And the way we do that is by taking whatever exponent might be present, m, and divide by the index, n. Okay? So it's going to feel weird. Trust me, you guys have never seen this before. So this is going to feel weird. But we can change radicals, roots, into fractional exponents. So just some simple examples to get going here. What if I gave you the second root of 9 and wanted you to change it to a fractional exponent? What if I gave you the third root of x squared and asked you to turn it into a fractional exponent? What if I gave you the 12th root of y to the 5th and I wanted you to turn it into a fractional exponent? How would you do that? Well, the radicand stays the same. So the 9 stays 9. The x stays x. The y stays y. So the radicand just stays the same. And then what we do is we create a fraction out of the two values, the exponent and the index. Whatever the exponent is goes in the top. Whatever the index is goes to the bottom. So let me choose a highlighter here. You can see the index on this one is a 2, then a 3, then a 12. So the index goes to the denominator, 2, 3, 12. And the numerator is the exponent. And the exponent is, on each of these, working backwards, the exponent on the y is 5. The exponent on x is 2. And the exponent on a 9 just sitting there by itself, the exponent on the 9 is a 1. And so what I'm telling you, for the first time that you've ever seen this, the square root of 9 to the first turns into 9 to the 1/2 power. The third root of x squared turns into x to the 2/3. The 12th root of y to the 5th turns into y to the 5/12. And the way we do this in advanced math, these pairs are actually going to be equal to each other. These pairs are actually going to be equal to each other, which seems really weird, okay? Because these exponents that we end up with over here, these exponents, no longer make sense as our usual exponents. Usually an exponent means repeated multiplication. So when I gave you guys something like 2 to the 4th power, that's just a way to write 2 times 2 times 2 times 2, repeated multiplication. Okay? Or 3 squared just means 3 times 3, right? What gets more confusing is what the heck does 9 to the 1/2 mean? Well, it no longer means repeated multiplication. It now means that that's a different way to write the square root of 9 to the first power. It's a different way to write that. Okay, so it takes some getting used to. All right, so feel free to pause the video and take a closer look at those examples. Maybe try some of those problems in your book where you have to switch from one to the other. And then what we're going to do is start to look at some of our fractional powers. So fractional or rational powers. And I want you to be able to evaluate some of these. And in fact, I'm going to start you off with a whole list. I'm going to ask you to evaluate 1 to the 1/2, 4 to the 1/2, 9 to the 1/2, 16 to the 1/2, 25 to the 1/2, 36 to the 1/2, and that's all I have room for, so I'm going to stop there. I'm going to ask you to evaluate, figure out what each of those are. Okay, now if you back up, the one I had given you earlier, 9 to the 1/2, remember that was going to be the same as the square root of 9 to the first. Okay? The square root of 9 to the first. That we just did that conversion. And of course, you know what this is. The square root of 9 is 3. 3. Okay? So what I'm telling you is anything, and I'm going to go with cloud, anything raised to the 1/2 power is equivalent to the square root of that thing. Anything to the 1/2 power is the same as the square root of whatever that is. Okay? So when I give you 1 to the 1/2, 4 to the 1/2, 9 to the 1/2, 16 to the 1/2, 25 to the 1/2, 36 to the 1/2, anything to the 1/2 power is the same as square root. Anything to the 1/2 power is square root. So what's 1 to the 1/2 power? The square root of 1 is 1. What's 4 to the 1/2 power? The square root of 4 is 2. We've already done this, but I'll do it again. 9 to the 1/2 is the same as the square root of 9, 3. 16 to the 1/2 is the same as the square root of 16, 4. 25 to the 1/2 power is the same as the square root of 25, 5. And 36 to the 1/2 power is the same as the square root of 36, 6. And I'm just going to do a couple more out loud. 49 to the 1/2, square root of square root, so 7. 64 to the 1/2, square root of 64, 8, and so on and so on. So anytime you ever see 1/2 power, that's going to be the same as square root. If you ever see 1/2 power, that's the same as the square root. Okay? The other one we'll ask you to use fairly often is a 1/3 power. And again, I'm going to start you off with a list of problems. 1 to the 1/3, 8 to the 1/3, 27 to the 1/3, 64 to the 1/3, 125 to the 1/3, 216 to the 1/3, and again, kind of out of room, so I'll stop there. So what do we do with the 1/3 power? Well, anything, so holiday tree to the 1/3 power, when I change that back to a radical, the numerator becomes the exponent, the denominator becomes the index, and the number becomes the radicand. So holiday tree to the 1/3 power is the same as the third root, cube root of holiday tree. So for the rest of your math life, anytime you ever see something raised to the 1/3 power, that's going to be equivalent to third root or cube root. So anything to the 1/3 power is cube root. So therefore, 1 to the 1/3 power is the cube root of 1. 8 to the 1/3 is the same as the cube root of 8. 27 to the 1/3 is the same as the cube root of 27. 64 to the 1/3 is the same as the cube root of 64. 125 to the 1/3 power is the same as the cube root of 125. 216 to the 1/3 power is the same as the cube root of 216, and so on. Okay? So really, to generalize, anytime we have something raised to a power where the numerator is 1, this then just simply becomes the nth root of star. So of course the same thing would be true of 1/4 power, 1/5 power, 1/6 power, 1/7 power, and so on. Okay, doing all right with that? Don't worry, it takes some getting used to, right? It's going to be tough the first couple of times you see it, but the more you see it, the easier it will become. Pretty soon it'll be automatic. Okay? Now, one quick thing before we go on to the next. Let me choose a different color here. One thing I just need you to notice, I highlighted it right here. Whenever the numerator is 1, it just becomes the same as the nth root of the denominator. Okay, so please notice all of the problems here had a numerator in the power of 1, so therefore they just became cube roots. I back up to the previous batch. The numerators in all these powers were 1s, so these just simply became square root questions. Next, what if the numerator isn't 1? What if I were to give you something like 8 to the 2/3? What if I were to give you something like 9 to the 3/2? What if I were to give you something like 4 to the 5/2? Right? What if I was to give you something like 25 to the 3/2? What if the numerator isn't a 1? What if it's a 2? What if it's a 3? What if it's a 5? What do we do when the numerator isn't a 1? And the answer is we make it a 1. So what I do with 8 to the 2/3 is I think of 8 to the 2/3 as being, I'm going to factor the 2 out, and that would leave me with 1/3. Would everyone agree that 1/3 times 2 is 2/3? Right? And the reason we do that, we factor out whatever the numerator is. We factor out whatever the numerator is. We do that so that inside, now, let me choose a different highlighter color. Now, the numerator in the power is a 1, and therefore when it's a 1, this just becomes, hey, what's the cube root of 8? And the cube root of 8 is 2. And then now using the power of 2, 2 squared is 4. So 8 to the 2/3 power is 4. So again, what we do with the top number is we factor it out, which leaves me with a numerator of 1. We factor the top number out, which leaves me with a numerator of 1. We factor the top number out, which leaves me with a numerator of 1. And again, let me choose my highlighter here. Numerator of 1, numerator of 1, numerator of 1. And then again, inside the parentheses, because we have a numerator of 1, this one just becomes the square root of 9. Because we have a numerator of 1, 4 to the 1/2 is the square root of 4, becomes a 2. Last one here, come on, pencil. Because the numerator is 1, becomes a square root, so this is just the square root of 25, which is 5. And then the outside power, 3 to the 3rd is 27, 2 to the 5th is 32, 5 to the 3rd is 125. So when the original numerator in the power isn't a 1, when it's a 2, 3, 4, 5, 6, 7, 8, 9, then what we can do is factor it out. We can factor it out. Okay? Alrighty. And I think I'm going to pause this video right here, and we'll finish off the rest of section 5.1 in the next. Okay, so hope you're having a good day, and then look for the next video to finish off section 1. See you later.